Okay, so we're at 11:38 and I will be starting the MIG meeting. Being that I'm both the host and the speaker, I'm going to have to introduce myself. So our speaker for today for the Math Interest Group is myself, Walt Meissner, giving a talk on the Riemann hypothesis. Earlier in the year, I came across a YouTube video by Kontorovich on the Riemann hypothesis. It was very well done and gave a history behind it and how it relates to prime numbers. The previous talk on the 3n+1 problem, and now the Riemann hypothesis, will be referenced by a MIG talk given by Al Hayo and is scheduled for next month. The talk on the Riemann hypothesis will be about 45 minutes in length and then followed by the YouTube video, which is about 15 minutes in length, and then followed by the question and answers. So now for the screen share. The topic for today is the Riemann hypothesis. The talk will have some introductory slides that will go into some depth on the topic. This will be followed by a short YouTube video by Kontorovich. I would like to thank Alex not only for making such intuitive video, but also for providing me with some reference links to the original papers of the mathematicians and also the details, mathematical details on this topic. I also like to thank Al Aho and John Maheda for the constructive feedback on the slides, and also John for doing a trial run of the presentation with me. A brief overview. The Riemann hypothesis is based on the Riemann zeta function that says that all zeta zeros on the complex plane occur when the real part of the complex argument S is equal to 1/2. The person who can prove this will win a $1 million prize from the Clay Institute. What we'll be covering is we'll show that there's an infinite number of prime numbers. We'll talk about the prime number theorem, the prime counting function, the zeta function for real numbers, the Riemann zeta functions for complex numbers, analytic continuation, a modified prime counting function, and a harmonic approximation to the modified prime counting function. And all this has significance for cryptography and quantum physics. Just a few basics to refresh people's memories. The natural numbers are the counting numbers, integers starting with 1. Composite numbers are positive integers formed by multiplying two smaller integers. Prime numbers are natural numbers greater than 1 and are divisible only by 1 in itself. So this doesn't include composite numbers. The sieve of Aristophanes has order n log n computational complexity. It eliminates composite numbers by leaving just the primes. So the first step is you build a sequence of integers and you start with the first prime, which is by definition 2. And you take multiples of 2 and cross that out in the sequence of integers. And then you advance to the next non-eliminated number, which will be the next prime. And then you go to step 1 and repeat and eliminate all multiples of that prime. So the pro of this method is it's a reliable method to find primes. The con is you need to find all the primes in increasing order. Now, in order to do this, if you do this on a computer, many times you're limited by the word length, which is 8, 16, 32, 64 bits or whatever. Unix has a routine called infinite precision, and it's basically just builds a very long string, and it's just a sequence of numbers, and so it's possible to do it for very large prime numbers. There's over the millennia, there have been several people that have generated formulas thinking they hit the jackpot by finding prime numbers. Formula 1 is Wilson's theorem. So it just says n is prime if and only if n minus 1 factorial plus 1 is congruent to 0 mod n. So what that means is if you divide by the left side by n and add 1, you divide the left side by n and the remainder is 0, then it's prime. So the complexity, if you just start in the middle somewhere is n factorial. But if you start at the beginning with the first prime and just work your way up, the order would be n. I tried this on a spreadsheet. Integers become floating point numbers by 15. To compute valid primes, I was only able to get to from 2 to 23, and after that there are many composite and prime errors. So this is probably a routine that needs infinite integer precision routines, which is just a string of digits. And there was no indication whether there's a point where this algorithm fails. Formula 2 generates it, and the formula is 6n, either +1 or -1, and it's used for primes greater than 3. The time complexity would be order n, and the first prime it generates is 5. So I tried this on a spreadsheet from 1 to 256, and it did find primes, but also included 31 composites. So it seems good, but in practice, too many non-primes show up. And then there's formula number 3. This is one that I may have read about back in the 80s, that somebody developed a formula, and when people were still doing it by paper and pencil, it seemed like this formula worked up to the point where they could verify the primes. But then somebody verified the next prime and found out that the formula didn't work. Now, I'm not sure if it's this formula or another formula, but its formula is n squared plus n plus 41. And it works for primes greater than 40. So in other words, n starting with 0, the time complexity would be n, and the first prime it generates is 41. So the primes from 2 up to 37 are known and easily verified, so you don't have to worry about them. I tried this on a spreadsheet, and sure enough, it validates primes up to 1601, where the input n is 39. But if you go to input 40, the next generated number is 1681, which is not a prime. So it fails after that. Okay, Euclid provided a proof that there are an infinite number of primes, and he did this in the first of 4 books called The Elements. So this is book 9, proposition 20, and it says, let's build up a list of primes, P1, P2, up to Pn, and let's multiply them together and make a product. And then let's let Q equal that product plus 1. So if Q can either be a prime or not. So if Q is a prime, then there's at least one more prime that's not in the list. And if Q is not a prime, then there's a way of determining if it should be in the list. And I'll just give an example. Let's take the first couple of primes, 2, 3, 5, 7, 11. And let's multiply the first 2. So 2 times 3 is 6. Add 1 is 7. That yields the next prime 7. You can see that. I'll just point on where I am on the view graph here. These are the primes we're working with. So we could generate another prime. If we then multiply by 5, we get 31. Multiply by 7, add 1, we get 2, 11. Multiply by 11 to that product, we get 23, 11. But then if we add 13, which would be in our list, this yields a number 30,031, but that has prime factors of 59 and 509. So even if the number it generates is not prime, it very quickly generates numbers that are prime. There's numerous other proofs by Euler, Erdős, and Furstenberg, and I won't get into them. Let's talk about the prime number theorem. So people have been looking at primes and trying to see how they propagate, as you go up in the integers. And so the theorem says the number of primes that are less than n are approximately equal to n over natural log of n. And so this sort of confirms an asymptotic distribution of prime numbers among positive integers. It formalizes the idea that primes become less common as they become larger, and it quantifies the rate at which this occurs. Now, what it doesn't tell you is, as you get higher up in the prime, sometimes you have primes that are, very close to each other. So there's things like the twin prime problem and stuff like that. Okay, so a little bit of the history. So people looked at a long time. So Fenkel, Vega, and Legendre looked at it, and they came up with pi of A equals A over capital A log A plus B, and they figured out they could best curve fit it with A equals 1 and B equals minus 1 and change. Gustave Lejeune Dirichlet used the logarithmic integral formula, which he called Li of x. And here's what Li of x looks like. So it's just the integral from 2 to x, 1 over natural log of x dx. And Chebyshev proved a weaker form of the asymptotic law. He says if you take pi of x, which would be the actual number of primes, and divide it by x log x, the limit as x goes to infinity would approach 1. And there are other people, Hadamard and Poussin, who also supplied proofs. Okay, let's talk about the prime counting function. So the prime counting function is defined as pi of x, which is equal to the number of primes up to some number x. So in 1796, at age 19, Carl Friedrich Gauss cataloged primes up to 3 million. The fact that he did that is pretty amazing by itself. People are not sure how he did this. They speculate he used the sieve method. And so basically he noticed that, as others did, that primes have a growth rate of x over log x. But he also noticed, because he went to such a high number of primes, that the best fit really is this logarithmic integral function Li of x. Now, the way the prime counting function works is, start off at 0. 0 is not a prime. 1 is not a prime. You go to 2. 2 is a prime. You jump up 1 unit. So that's your first prime. You go to 3. 3 is a prime. You jump up to 2. So now you have 2 primes. You go to 4. 4 is not a prime. 5. 5 is a prime. So you go up to 3. So that's how the prime counting function works. And if you look on the right, there are 2 graphs. The top is pi of x divided by x over log x. The bottom is pi of x divided by the integral, the logarithmic integral. And it just shows you that the integral approaches 1 much earlier at 10 to the 4, whereas the x over log x is still not at 1 with numbers as high as 10 to the 24. Okay, taking the prime counting functions. If here we only looked up to numbers up to 10. So the upper left graph looks at numbers up to 100, and you can see it staircases up, and it sort of falls off a little bit. So it doesn't follow an x equals y line. So it falls off from that. And if you look at it up to 3 million, it looks like a straight line at this scale because you can't see the staircase steps anymore. So there's other people that have looked at it, and they've come up, I just provide this for reference. They came up with an exact form, and the exact form uses the logarithmic integral, also uses another function, Möbius function, which results in +1, -1, or 0, given some condition. And I have this feeling that this corrects for any inaccuracies by the integral formula. And there's other counting methods done by other people. Okay, let's talk a little bit about harmonic series. Harmonic series are infinite series by summing all positive unit fractions. Leonard Euler worked on various forms of the harmonic series. So the first one here is just the sum of 1 over n, where n goes to 1. Sum from 1 to x as x goes into infinity. So you get 1, 1 over 1, 1/2, 1/3, 1/4, 1/5, so on. And this diverges, and there's a number of proofs that do that. It's not too hard to prove. You also looked at 1 over 1/2 to the nth power, with n going from 0 to infinity. And if you look at that, you get 1, 1/2, 1/4, 1/8, 1/16, and graphically you can show that it easily, it converges to 2. Then he looked at other powers of n. So 1 over n to this, to second power, to the fourth power, to the sixth power, to the eighth power. And he came up with this amazing result, but there's a little bit of a story behind it. The amazing result is, 1 over n squared summed up to infinity equals pi squared over 6. Okay, and the fourth power, pi to the fourth over 90, sixth power, pi to the sixth over 945, and the eighth power, pi to the eighth, 9450. So how can this be? How did pi show up here? So, so there's a little bit of a story behind this. And the story is, Basel, Switzerland was the hometown of Euler, but he worked in St. Petersburg. And the Bernoulli brothers also lived in Basel, Switzerland. They couldn't solve the problem, and they gave it to visiting mathematicians. And numerous mathematicians failed at solving the summation, and thus it became known as the Basel problem. Euler happened to visit the Bernoulli brothers in Basel and was able to solve this. He became an instant celebrity in the math community, and his original derivation. And one of the things he used is, in the original derivation, is that he had certain observations about prime polynomials, and he assumed they also hold true for an infinite series. Thus, this proof is considered non-rigorous by mathematicians. And the proof is an amazing feat of algebra. So what he did is, he was familiar with the Taylor expansion, which had been developed previously, and he took the expansion of sine x, and here's sine x here, and here's the closed summation formula. And so this just becomes x to the 1 over 1 factorial, x to the 3 over 3 factorial, x to the 5 over 5 factorial, and so on. And he decided to divide this through by x. And when you divide sine x by x, you get what's called the sinc function. And here's a graph of what it looks like. So at 0, it's 1, and then it sort of oscillates to the left and to the right in a decreasing mode. And if you divide through by x, you get 1 minus, oh yeah, I forgot to mention, the sine x has alternating signs, so it's plus, minus, plus, minus. So you get, dividing through by x, you get 1 minus x squared over 3 factorial, plus x squared to the 4 over 5 factorial, x squared to the 6 over 7 factorial. And, what Euler knew is that, a polynomial with finite powers has n roots. So he can restate this, the polynomial, as some constant minus x, and have 5 of them with 5 different constants. And all you need to do is find those 5 constants. So the property he knew is it had 1 at 0, and it had roots at pi, minus pi, 2 pi, minus 2 pi, and so on. And so it really functioned like a cosine function here. You can see this oscillating to the left and to the right. And so he set up his equation, sine x over x, put the products on the right side, and he noticed that 2 of the products, that each pair of products are really they form the difference of squares. So he could very easily, condense this and get powers of x squared, all the way down the line. And if you look at the original equation, sine x over x expands to 1 minus x squared over 3 factorial plus the other terms. And if you were to multiply this product out further, you'd obviously get powers of, of x to the 4, x to the 6, and so on. But if you just look at the x squared term, you can collect the x squared terms by Newton's identity. So you have x squared over pi squared, and then if you notice these products, the coefficient here is 1 over pi squared, 1 over 4 pi squared, 1 over 9 pi squared. You can pull this pi squared out. You're left with 1 over 1, 1 over 9, 1 over 4, 1 over 9. And lo and behold, this series here is exactly what you started off with. So it's the summation of 1 over n squared. So if you cross multiply and clean this up, you get that this series is equal to pi squared over 6. Now what he decided to do is generalize it and call these summations zeta of s. And so if you take zeta of s and which would be 1 over n to the s summed up, and so zeta of 2 would equal pi squared over 6 rather. So this was an amazing result, and it propelled him into mathematical stardom. Now, Euler later proved this more rigorously with Fourier analysis a century before Fourier, and this proof can be made more rigorous with the Weierstrass-Hadamard factorization theorem for entire functions. And other people have provided other proofs. So let's go to the next one. Now, Euler, when it comes to this function, the summation of 1 over n to the various powers of s, he proved that the zeta function converges only for s greater than 1. And Euler was not one to rest. He continued to develop this zeta function. And he discovered that it could be expressed as an infinite power of an infinite series, one for each prime number. So this was a really amazing result. I mean, now prime numbers got into here. So here's zeta of s. This is the closed form which represents this product down here. So it's a product of numbers that include primes from 2 to the maximum. And you have this series summation, p to the ms, where p is the prime given by the product. And you multiply this out from 0, the summation from 0 to infinity. So here's the prime 2, and here's the prime 3 and 4, 7, 11, and 13. And this, he now showed that this is equal to the summation of 1 over n to the s. So this was really an amazing result. And I think he and other mathematicians rewrote this as a simple multiplication product, 1 over 1 minus 1 over p to the s. So that's another way to formulate it. Okay, just to refresh people's memory on complex numbers. Complex numbers extend real numbers into the imaginary plane. So here you have complex z equals real a plus real b times I. So I is defined at I squared is equal to -1. So I is the placeholder for I equals square root of -1. So Riemann took the zeta function. He says, well, what would happen if zeta of s, if s was complex? So s now became sigma plus tau I, a complex number. And actually, before I go into this, this graph on the right just shows you a line in the complex plane. So the x-axis is the real axis, the horizontal axis, the vertical axis is the, or the y-axis is the imaginary axis. So here you have a line going from 0, 0 to z equals a plus bi. And so this is, it falls down to a on the real axis, and it falls over to b on the imaginary axis. So it should come as no surprise that, you know, theta of a complex number converges only when the real part of S is equal to greater than 1. So now you have this complex plane, and only the right half greater than 1 has convergence. So what Riemann did is he used something called analytic continuation to get around this limit, to get around this. So so this extends the domain of the complex zeta function. It allows mapping of the function to the rest of the complex plane. And there's really two functions that work, the original zeta function and the Riemann zeta function. And here's a diagram of how you go about doing this from a visual point of view. So the upper left, which is diagram 1, you have the complex plane, and you have a grid from 1 going to the right. And you can map points here and compute the zeta function here. And what you want to do is you want to take the points to the left of 1 and extend it to the grid to the left. All right, so what's needed is to apply analytic continuation. So the plot for number 3, they took the right-hand side of 1 and applied a function to it to which will be used for analytic continuation. And what it does is it curves the grid, so you have like circles and radiating lines. Now, if you take the function that's on the right side and you apply it to the left side, you get two symmetrical functions. So one is zeta of s, and the other one is zeta of 1 minus s. And there's a couple of things I like to mention about analytic continuation. Is any extension to the rest of the complex plane possible? And the answer to that is yes and no. And it's yes, you can apply any function, but no, because there's a requirement that the function has to be analytic, just like the original zeta function. And what that means is it has to have a derivative everywhere, and that results that one and only one extension is possible. The other thing is there's something called, it results in an angle preserving property. So any two intersecting lines at some angle will retain that angle after the transformation. And if you look at these radiating, these circular lines and the radiating lines, you know, the grid has a 90-degree angle between the horizontal line and the vertical and the vertical line. And if you look at the intersection of any of these radiating lines with these circular lines, the angle here is also 90 degrees. And so, and most functions are actually analytic, and this is why the extension is called analytic continuation. Okay, now I'm not going to go through this in much detail, but I just want to show people what that function actually looks like. So they have zeta of s, and the summation of 1 over n to the s power. And they've rewritten this in terms of the gamma function and this integral. So the gamma function itself is also defined as an integral, and it applies when the real part is greater than 1. So it really only applies to the right half when of a vertical line at 1. And the other thing I like to mention is that the gamma function is also called the Stirling's approximation. You may have seen this in some course where, you know, the factorial of n factorial of n minus 1 factorial is equal to gamma of n. So it was a quick way of getting finding out what large factorials are. Anyway, so the zeta of S has been rewritten. It's really like two functions. So here you have zeta of S here, and on the right side you have zeta of 1 minus S, and in between you have the gamma function, and you have sine pi over S over 2, 2 to the S, and pi to the S minus 1. And now, one of the things about this function is that this function will have zeros, but there's a bunch that are called trivial zeros, and the trivial zeros are when S equals minus 2n. Okay, so if you take minus 2n, you plug it into this sign, or into the argument of the sign, you'll get pi. You get minus pi, minus 2 pi, minus 4 pi. And this is exactly where sine is equal to 0. So these are called the trivial zeros, and this is not the zeros that they're looking for. Now, the other thing is, you may ask, well, shouldn't there be zeros on the right-hand side? Pi, 2 pi. And it turns out that the gamma function has poles at, which cancel out the zeros of the sine function. So that's why you don't see the zeros to the right of it. And here's just a picture again of the complex plane with the analytical continuation here. Okay, so what is the Riemann hypothesis? 1859. Trivial zeros are at the negative integers, S equals minus 2n. I mentioned that already. And they can show that the rest of the zeros, the non-trivial ones, will have the real part of S that lie between 1, 0, and 1. So here's S equals 0, the real part, and here's S, the real part of S equals 1. And so they can basically show that there'll be zeros somewhere in this region. Now, the Riemann hypothesis states that all non-trivial zeros will occur when the real part of S is equal to 1/2. So this region here, where zeros could occur, is called the critical strip, and the line where the real part of S equals 1/2, this is called the critical line. So this is this line right here, and there's dots for wherever, for the value of S wherever theta of S was equal to 0. Okay, so let's talk about graphing the output of the Riemann zeta function onto the complex plane that includes analytic continuation. With values of S, the function loops around and falls on the 0, 0 coordinate, making a zeta 0. So if you see an animation of this, it's quite beautiful to observe. So it starts here and it loops around like this, goes through a 0, loops around again, goes through a 0, loops around again, goes through a 0. And when it goes through the 0, the real part of S will be 1/2. And the question really is does that happen in each and every case? So now I'll talk about the modified prime counting function. So instead of doing a step size of 1, let's do a step size of log of the prime number. So when you step up by 2, you'd be stepping up by log of 2 instead of 1. And we do 3, log of 3 instead of 1. So this is what that looks like. And so just a bit about harmonics. People that are familiar with the Fourier series know that you can take the sum of sine waves, and by choosing which sine waves you add up, you can create a square wave, you can create a triangular wave, and you can generate any wave you want. So even very and you can take, let's say, some music, which will have, you know, just a wave representing the music, and you can decompose that into a series of sine waves of different amplitudes and different frequencies. So you can basically do that. You know, that's how you would deconstruct a musical passage. Anyway, so what they noticed is if you plot the harmonics of when the Riemann Zeta function is 0, if you just do the first harmonic, now if this axis, this is the modified prime counting function, the x-axis is the integer series, and if you just do the first harmonic, you get a wavy function that sort of follows this staircase prime counting function. And if you take the first 30 harmonics, you notice it begins to curve fit this staircase, this prime counting function, even better. And it only seems to fall apart a little bit at 30. And it's presumed that if you take more harmonics, it'll be a tighter curve fit. So summing all the harmonics of zeta 0 should match the log prime counting function. Okay, so now I'm going to cover something that's actually not covered in the video. You know, people say, well, you know, let's say given that is true, what else can we do with the zeta function? Well, one thing that they did is let's generalize it. So we have the generalized Riemann hypothesis, and instead of zeta of S, we now have L of capital X and S, and X is called the Dirichlet character X, which is a multiplicative arithmetic function. So the argument is actually a function now, and it's replacing the numerator, which used to be 1, by a function of X. And I'm not really going to go into this very much here. You know, there's a consequence of the generalized Riemann hypothesis, and one is the Dirichlet theorem. So this is a prime counting function that has X and 2 other arguments, A and D. And I'm not going to go into this much either very much. So there's actually numerous theorems and conjectures that follow from the generalized Riemann hypothesis functions, and this is another reason why they would like to see that conjecture proven to be true, because if it wasn't true, all these other things would fall apart. Okay, so what is the connection to cryptography? The zeta function relates to integers to primes in a new way. Summation containing integers is equal to the infinite product of an infinite series, 1 for each prime number, as mentioned before. So it encodes specific information about prime numbers. And I guess question is, could it be used to find prime factors more efficiently in cryptographic algorithms, or could it be used in some other way yet to be discovered? Let's talk about the connection to quantum physics. You know, at first you may wonder how it is connected, but one thing that wasn't talked about is what is the spacing of the points where the real part of S is equal to 1/2? Are they regularly spaced? Do they bunch up? You know, how does that work? Well, there is the Hilbert-Poyak conjecture, and it says that the zeros of the Riemann zeta function correspond to the eigenvalues of a self-adjoint operator by means of spectral theory. So I'm not going to go into that, but there's a physicist, Freeman Dyson. He worked with random matrix theory for nuclear physics, and he was modeling the nuclei of heavy atoms. And another mathematician physicist, Eugene Wigner, postulated that the spacings between lines in the spectrum of a heavy atom should resemble the spacing of eigenvalues of a random matrix. And one day, I think Freeman was at Princeton, and Hugh Montgomery visited him, and And Hugh Montgomery said, well, in number theory, distribution of zeros of the Riemann zeta function can be modeled by eigenvalues of certain random matrices. And they started talking about each other's work and what kind of mathematics they were using to do that. And they realized, there was a high correlation. It was very similar what they were doing. So somehow the Riemann zeta function applies to quantum physics. And the other thing is, as I was researching it on the web, it's also been used to explain the fine structure constant, which is something that happens in the subatomic world. Okay, so here's some of the contributors. We have Euclid, we have Leonhard Euler, we have Johann Carl Friedrich Gauss, and we have George Friedrich Bernhard Riemann. And unfortunately, he only lived to be age 39 because he had health problems and he eventually contracted tuberculosis, and he was going back between Italy and Germany, and I think he died in Italy. And we have the person that did the video. So he's a Rutgers professor at Rutgers University. He teaches analytic number theory, L functions, which I mentioned in the one view graph, and two other areas which I'm really not familiar with. Okay, so in summary, the Riemann hypothesis says that all zeta zeros on the complex plane occur when the real part of S is equal to 1/2. And if you can prove this, you can win the Clay Institute Prize. And we talked about the fact that there's infinite prime numbers. If it was finite, you could probably solve the Riemann hypothesis easily. And we talked about the prime number theorem, prime counting functions, zeta for real numbers, Riemann zeta function for complex numbers, analytic continuation to map it on the whole complex plane, the modified prime counting function with a log p step size, and the harmonic approximation to the modified prime counting function. And we talked about the significance to cryptography and quantum physics. So that is the end of that. And let me just check. Okay, so Bill here, he had a comment in chat. He says, for analytic continuation, I believe you need the derivative to be continuous inside some arbitrary small circle. Okay, so we'll have him talk during the Q&A part. Okay, so let me exit this here, and I'll start the video.
When you look at this, what do you see? To me, this is one of the most beautiful, fascinating, and frustrating things I've ever seen. That's because I'm a mathematician, and these hypnotizing curlicues have haunted people like me for 150 years. What we're looking at is a glimpse of the Riemann hypothesis. It's one of the most important, if not the most important, unsolved problems in all of mathematics. You may have heard about the Riemann hypothesis because it's one of the Millennium problems of the Clay Institute. What that means is that the person who solves it not only achieves immortality in mathematics, but also wins a $1 million prize. But there are other reasons to care about the enigma that is the Riemann hypothesis. If the hypothesis is true, it would solve a mystery as old as math itself. That is, the mystery of the prime numbers. Countless theorems in fields as far apart as cryptography and quantum physics assume that the Riemann hypothesis is true, which means that we have a lot riding on this single unproven statement. So what is it? What is the Riemann hypothesis? Why has the search for a proof become something of a holy grail for mathematicians? And what do these strange curlicues have to do with all of this? My name is Alex Kontorovich, and I'm a professor of mathematics. I'll serve as your guide as we explore the Riemann hypothesis. In order to build a somewhat sophisticated understanding of this hypothesis, what I'm going to try to do is mention some slightly advanced concepts. Now, you don't need an advanced degree in mathematics to go on this journey with me. What I'm going to do is try to lay the groundwork, step by step, in a visual and intuitive way. So, To begin, let's venture into the chaotic and elusive universe of prime numbers. This is Factor City, where the primes are literally the building blocks of all numbers. Now, every whole number is a building, and it's been constructed out of its primes. The one-story houses are exactly the primes. Now, thanks to the ancient Greek Euclid of Alexandria, we know that the one-story buildings keep going on forever, if you can walk that far. But depending on where you're standing, you might want to know, how many one-story buildings do you see around you? This is what we want to understand about the prime numbers and what we currently don't. You see, the prime numbers seem to just pop up randomly among the natural numbers, all the way out to infinity. In the late 1700s, mathematicians were really starting to wonder whether it was possible to predict the places where primes would appear. Now, a teenage boy named Carl Friedrich Gauss was especially obsessed with taming the primes. He calculated massive tables of primes, going all the way up to 3 million, and looked for patterns. We can see the data that Gauss collected on the prime numbers by using something we'll call the prime counting function. The graph of that function will show us exactly where the prime numbers appear as the numbers get bigger and bigger. So the graph stays flat until you hit a prime, and at that point it jumps up by 1. Here's what the graph looks like out to 10, and out to 100, and now out to 3 million, as far as Gauss went. At this scale, those bumps we saw early on have smoothed out, leaving a pretty pleasant curve. When Gauss looked at this data, he asked himself, is there some other function that I know that has pretty much the same graph? Now, as luck would have it, at around the same time, Gauss was also playing around with logarithm functions. You might remember that a logarithm is a function that undoes exponentiation, much in the same way as division undoes multiplication. What Gauss noticed was that the graph of something called the logarithmic integral function, that's a function whose slope is 1 over log x, looked suspiciously similar to the graph of the prime counting function. Here's what they look like together. You can see why Gauss made the connection. At this scale, they're so close, you can't even distinguish them. To understand what the slope of 1 over log x has to do with prime numbers, let's pay another visit to Factor City. What Gauss imagined was that if you're standing at address x, and you look left and you look right, the proportion of one-story buildings, that is primes, that you would see around you is roughly the same as 1 over log x. This suspicion became known as Gauss's conjecture. After Gauss formulated this conjecture, his student Bernard Riemann went on to do something absolutely incredible with it. But to understand what Riemann did, we first have to go back in time a little bit to meet someone else. This is Leonhard Euler, one of the world's first students of calculus. Later on in his life, he wrote many influential textbooks and standardized the modern math notation that we still use to this day. If you've ever written something in standard function notation, like y equals f of x, well, you can thank, or perhaps blame, Leonhard Euler. In Euler's time, mathematicians were trying to understand the general structure of infinite series. What that means is, you're trying to add up an infinite sequence of numbers, like 1, a half, a quarter, an eighth, and so on forever. Sometimes that total sum is a finite number, which we then call a limit. If a series has a limit, we would say that the series itself is convergent. In this series, our limit is 2. On the other hand, if we were to add, let's say, 1 plus 1 plus 1 plus 1 plus 1 forever, well, that sum would eventually become larger than any finite number, and so we would say that that series is divergent. Sometimes it can be rather tricky to tell if a given series converges or not. So for example, this series, which is called the harmonic series, turns out actually diverges, even though the terms themselves are getting smaller and smaller. This is really rather not obvious, and takes some mathematical gymnastics to verify. Now what about this series, the sum of 1 over the squares of all the positive integers? It wasn't hard for mathematicians to show that this series does indeed converge, but the question was, what is the exact limit? Euler shot to mathematical superstardom when he solved this problem. What he realized and proved is that the limit is pi squared over 6. Isn't that weird? What in the world does pi have to do with the squares? Well, that's another story for another time. So, full of adrenaline from his early victory, Euler kept going. He found the limits of the sum of 1 over the positive integers to the 4th power, and to the 6th power, and to the 8th power. Now let's try to study all these series at once. Let's write s for that exponent. When we do this, we define what's called the zeta function. In other words, zeta of 2 is the sum of 1 over the squares, and zeta of 4 is the sum of 1 over the 4th powers, and so on. Euler proved that all of these converge, but only when s is greater than 1. But here's where things got really interesting. Euler discovered that the zeta function could be expressed as an infinite product, one for each prime number, of an infinite series. Here's what you do. For each prime number, you add up 1 over all the powers of that prime to the s. If you multiply all those series over all the prime numbers, you get the zeta function. Euler's discovery hinted at an intimate connection between the zeta function and prime numbers, but it would take another 100 years for the full meaning to reveal itself. And that's when our friend Bernard Riemann would make a major breakthrough in prime number theory. And that breakthrough would potentially allow us, for the first time, to understand the profound mysteries of prime numbers. So Riemann, he's born in 1826 in modern-day Germany. He's an absolutely spectacular and innovative, prolific mathematician, and among other things, his novel approach to geometry actually lays the mathematical groundwork for Einstein's theory of relativity. Riemann was also one of the founders of complex analysis, which is a branch of math that studies functions with complex inputs and outputs. And he realized he might have something new to say if he studied from that point of view Euler's zeta function. You might remember that the square of any real number is positive, so 2 squared is 4, but negative 2 squared is also 4. So there is no number whose square is negative 1. It turns out that it's really rather useful for mathematicians to have a number whose square is negative 1. So what did we do? We just made one up. We called it I for imaginary. So whenever you see I squared, what that means is you should replace it with negative 1. This means that any real multiple of I, like 3i or 2i, these are all imaginary cousins of the real numbers. When you take combinations of real numbers and imaginary numbers, you get something we call a complex number. Complex numbers might look like two numbers, but they're actually just one number expressed as two parts, the real part and the imaginary. The thing is, these imaginary and complex numbers, they aren't imaginary at all. They're just the natural extension of our usual number system from one dimension to two. They're plotted in what we call the complex plane, with the real part going left to right and the imaginary part up to down. Once you have these complex numbers, you can study complex functions. That is, functions with inputs and outputs living in the complex plane. And so, armed with the power of complex analysis, Riemann opened up a whole new perspective on the world of mathematics. Riemann wondered, what would happen if you allowed the zeta function to take complex inputs? That is, he allowed s to be a complex number. So let's take the complex exponent s equals 2 plus 3i, for example. We can plug it into zeta, and the function will look like this. Now, if we add each term one at a time in the complex plane, we can see how the series begins to spiral beautifully. So, Riemann had successfully accomplished what he set out to do. He extended the zeta function to the complex plane. But just like Euler, Riemann found that the function only converged when the real part of s was greater than 1. Now Riemann had a brilliant idea. He realized it was possible to extend the zeta function to the rest of the complex plane. Riemann used a technique called analytic continuation, which allowed him to break open the hidden potential of the zeta function. Now, analytic continuation is an advanced concept in complex analysis, but it's possible to make sense of it intuitively. You can think of it as a logical problem-solving method to extend the domain of a function. In order for Riemann to fill in the missing part of the domain in Euler's zeta function, he had to create a brand new function. This function would take the same values as the zeta function, where they both converge, but it had to make sense everywhere else on the plane too. So the secret to analytic continuation is that there are really two functions at work at once. One is the original zeta function, which has limited scope. But the other is this new function, the Riemann zeta function, which extends beyond the domain that Euler defined. Remember this? Now we can take a closer look at it and finally begin to understand its mysteries. You see, when Riemann extended the domain of the zeta function, something kind of amazing happened. In the new territory that Riemann uncovered, suddenly the zeta function can be seen crossing through the origin. What that means is, for some inputs, the zeta function evaluates to 0. We call these places the zeta zeros. Some of the zeta zeros are easy to explain. When you input a negative even integer, the zeta function equals 0. But we don't need to worry about these so-called trivial zeros. It's the non-trivial zeros that we need to talk about. These other zeta zeros exhibit a very compelling pattern, and that pattern is the central theme of the Riemann hypothesis. All of the non-trivial zeros lie inside a single region called the critical strip. This is where the real part of S is between 0 and 1. Riemann proved that there are infinitely many zeros to be found in this critical strip. But here is the most important takeaway from Riemann's groundbreaking 1859 paper. Riemann hypothesized that all of the non-trivial zeros will lie not just somewhere in the strip, but on a single vertical line, smack dab in the middle. We call this the critical line, which is where the real part of S is exactly 1/2. This is exactly the hypothesis that now bears Riemann's name and the $1 million bounty. Now at this point, you might be wondering, why does the location of these non-trivial zeros matter? And what does all of this have to do with prime numbers? I don't blame you. Let me show you exactly why Riemann's hypothesis is of such profound consequence to number theory. And let me do so by sharing Riemann's final discovery. Remember Gauss's prime counting function from the very beginning of the video? Well, for technical reasons, we're going to slightly modify it right now, but don't worry, we'll preserve the essence of the function. Instead of stepping up by 1 every time we see a new prime number, which we'll call p, let us step up by log p. And we'll also do the same when we encounter p squared, np cubed, and p to the 4th, and so on. So let me try to explain why we're doing all of this. Riemann found a surprising connection between this modification of Gauss's conjecture and his new zeta function. He discovered a wave that corresponds to the zeta function at s equals 1 and showed that Gauss's conjecture would follow if only you could show that this wave was the fundamental frequency, which means that it more and more closely approximates the prime counting function as they both grow to infinity. So here's what the prime counting function looks like with that wave that Riemann discovered. Riemann realized that the zeta zeros were exactly what he needed to adjust this straight line to match the jagged counting function. Every time he added a zeta zero, it contributed a harmonic. Here's what the first harmonic looks like when we add it on. It ever so gently tries to smooth out the wiggles of the modified prime counting function. What happens when we plug in the second zeta zero? A little better, right? What about the first 10? Or the first 30? Or the first 60? You get the point. Riemann was able to rigorously prove that if you add up all the harmonics of the zeta zeros, all infinitely many of them, you get a perfect match to Gauss's modified prime counting function. So, Riemann's hypothesis showed that the distribution of prime numbers can in fact be predicted. The location of prime numbers is profoundly connected to the location of these non-trivial zeta zeros. This means that if the Riemann hypothesis is indeed true, it would tell us everything we could possibly have a right to know about the distribution of prime numbers. Needless to say, Riemann was unable to prove the full hypothesis. In other words, neither he nor anyone since has been able to show that every single non-trivial zeta zero lies on that critical line. At one point, a massive computing project checked over 1 billion non-trivial zeta zeros every single day. The computer was looking for a single errant zero. If it found just one, then the Riemann hypothesis would fall apart. In the end, of the 10 trillion zeros that the computer checked, every single one was on the critical line. But if you see a pattern holding again and again and again, it's still impossible for machines to check it all the way to infinity. So brute force computation will never resolve the Riemann hypothesis. That means there's still only one way to be sure of it, and it's the same way that the ancient Greeks did their math. Rigorous, absolute mathematical proof.
Okay, so I'm stopped sharing and we can go to questions and answers. Please raise your hand if you'd like to say something. Okay, our first person is Al Aho. Please unmute yourself.
Thank you, Walt, for a brilliant talk. When I hear talks like this, they always remind me about how little I know about number theory. So it was another exposure to the mysteries of the prime numbers that I've always been intrigued by and still mystified by. I have a few questions. Could you say a few words about the debate between whether the number 1 should be a prime number or not? My understanding is that a long time ago it was considered to be a prime number, but now most mathematicians don't consider it to be a prime number.
Yeah, I kind of wondered about that myself because, I guess when I was in grade school, I think they said prime 1 was a prime, and now it appears it's not. And I guess if you use the definition that it's divided by, well, I guess in theory, I guess one way to look at it, I guess it could be, but I really haven't come across anything that, elucidated on that.
I have a couple of other questions. They're kind of trivial, but historical. Why did Riemann call his function the zeta function?
I think it was actually Euler that called it the zeta function, but I can't be entirely sure of that. So when Riemann applied complex numbers to it, it became the Riemann zeta function. So he kind of owned it from that point of view.
Okay, and one note on, you mentioned, or Kontorovich mentions that there may be connections between the zeta function and quantum theory. In one of the papers that I looked at, there was a talk about the moments of the zeta function. What is a moment of the zeta function?
I mean, that's a good question. I mean, I've seen moments for probability defined, and I guess it's sort of like a transform where you have an exponential inside the integral, and you can get out the parameters of a probability function. I'm not exactly sure how that works for the zeta function. I mean, I did see a note somewhere about somebody talking about the moments of it, but I haven't seen any mathematical formulation for that. But, it's an interesting question, though. Something that I wondered as I saw the moments being described, mentioned.
Okay, thank you again, Walt, for a brilliant talk.
Okay, thank you very much. Let's just see. Okay, so the next person is Jim Landwehr. Would you please unmute yourself?
Now I'm unmuted now.
Yes, you are.
Just more of a comment. I recall back in Bell Labs days, there was a mathematician, Andrew Lisco. I think it was in the 80s, and he might have or must have been part of this computing project that they talked about in the video, because I know he was doing some sort of computing and sophisticated stuff. And I didn't really know much about it at the time, but it's kind of interesting. It must have been a mammoth project, and I presume he was part of that as opposed to doing his own thing. I don't know if Al or anybody else from around then came across it. The other thing is that it just takes me back to my undergraduate days, where I guess I learned a little bit about complex analysis. And then never went back to it. But it was interesting to recall that stuff in this analytic continuation. So thanks for an interesting talk. And if anybody else knows about this computing project, I'd be curious.
Did you actually use analytic continuation in any of the stuff you did?
I can't remember. When I was an undergraduate math major, I was advised that a good course to take would be complex analysis, as opposed to one of the other courses, because it was sort of so different and so neat and off the wall and whatever. And I took it, and I guess I learned it at the time, but that was more than, that was more than 50 years ago, maybe more than 60 years ago. And whether I certainly don't remember it. Whether I used it or not, I suppose maybe I did, but I don't know.
Okay. The next person is Bill Heary. Would you please unmute yourself?
Hi, Walt. Thanks for the talk. It's very interesting. I can actually address a few of the points that Alejo raised. One, the idea of whether one is a prime or not, I think that became a convention just because if you don't say it, then so many theorems about prime numbers would say all primes except 0, except 1. So it's just easy to say 1 is not a prime, and that gets rid of that nomenclature issue. Second thing, the bit with Freeman Dyson and the matrix, the random matrices. My understanding from Dyson's own book is that it was a casual encounter at the dining room of or lunchtime at the Institute for Advanced Studies in Princeton, which is not part of the university. Then in those luncheons, whoever shows up, and it was like the old days at Bell Labs where you get somebody who's a specialist in something else and wind up having conversations. And he was listening to the person who was working on the Riemann hypothesis talk about these randomized matrices in whatever language he was using, whatever terminology. And Freeman said, wait, that's exactly what we do in quantum mechanics, the exact same kind of randomized matrices. So they kind of worked together because they had some of the same tools involved. I don't know, and it might be, but I don't know if there was actually feedback to enhancing quantum mechanics by using work from the Riemann hypothesis. Let's see. Andrew Odlyzko, I knew him in Bell Labs in the 90s. I don't know if he was involved with that particular computing project. I know he was involved with another one, which was the challenge to factor, I think it was a 1,000-bit or more integer as a challenge with regard to the early days of factorization. Was related to prime numbers and security on the web, the RSA algorithm. And so I know he was participating in that pretty heavily. He might have been participating in this one also. If anyone wants to follow up with him, as of a couple of years ago, Andrew was at the University of Minnesota, where he was running some kind of a center related to computer security. He worked a lot in security and cryptography when he was at Bell Labs. The last and the most interesting point is the one about analytic continuation. I studied that many years ago at a graduate level, so I hopefully remember what's important about it. The idea of analytic continuation is that if you have an analytic function, which means a function which has a continuous derivative in some region of, within any circle of non-zero diameter, it turns out that that little bit of information is incredibly useful. And it will mean that all derivatives of that function exist, not just the first derivative, but all the derivatives, and they're all continuous, which certainly doesn't happen on the real plane. So that's an interesting fact. With regard to analytic continuation, the way that would work is if you have some function that you have that's analytic, you do the Taylor series expansion of it, and you will find that it converges until you get to some point, unless it's a very trivial function. And then you can prove that within that circle of convergence for the Taylor series, it's going to be analytic. So it's now expanding the circle where it was originally analytic, where you knew it was analytic. But now you can go and you can take another point, let's say towards the boundary that in a different direction within that circle, do the Taylor series again, and you start adding another circle where it's going to be analytic. And you can keep going like this. And you could see the circles on the graphs that Walt showed. As you do that, you wind up covering a much larger area, potentially the whole pole, the whole plane, or for a trivial case, or in the case of something with a single singularity, one point where the series doesn't converge, you could wind up covering the whole plane except for that one pole. The other interesting thing is that all the graphs for this work with complex functions of complex variables, you really need four dimensions to really describe and to visualize. So the visualizations usually try to go, looking at the complex plane and what the values are, but just like absolute value of the values, or there's other ways of trying to visualize it, but it's always difficult. But one of the things that can happen is if you do something like the analytic continuation of the square root of x, excuse me, square root of z, in 4 dimensions, that winds up having 2 planes. And if you do the analytic continuations, it'll wrap around the pole, which is the 1 point, is it square root of z? It might be square root of 1 over z. I haven't looked at this for years. But it will wrap around the pole at 0, and then it'll, and then the first of the cases where through wrapping around 0, a pole point, go to an infinite number of different layers in the analytic plane, the analytic continuation. So it's a really fascinating subject, which would be a difficult talk, but at some point I was actually looking at that as a possible talk for this course, for this series.
So I have a question for you.
Yeah.
When they're doing that graph, where it circles around and goes, the zetas are going through 0. What values of S are they using, stepping through to do that? Do you have a sense of what that should be?
I assume the S is the point in the complex plane. So it's the
Yeah, but you have a real part and you have an imaginary part. How are they stepping through that number?
No, I think that what you saw on the graph was the plane, and then the curve was drawn through it, looking at the value zeta of S, where S is in the complex plane. But remember, that critical line is the line of S equals 1. So you don't care about the complex part of it. So in theory, those graphs should really be 2-dimensional things, not just lines, I would think. But again, it's a question I haven't looked at in detail, but my understanding would be that because you're looking at when the 0 is the zeta function, and it's always on this line where the S equals 1 that you're trying to prove, it doesn't matter about the complex parts, even though if you were going to look at the whole curve properly everywhere it went, not just for looking for the zeros, I think it'd be okay.
Okay.
But I'm not, again, I haven't looked at the Riemann hypothesis for several years, so I'm not really positive about that, but that was my interpretation when he showed that graph.
Okay. All right. The next person is Bill Tittle. Please unmute yourself.
Yeah, I love this group. It's really, really fun. But I always wonder, what can you do with this stuff? See, I was a chemical engineer, and the only time I got into zeta functions in a chemical engineering world was in the subject of process control, which is a simple-minded thing, like your thermostat at home, And I think in the world of Bell Labs, which is all about communication, signals, and all that stuff, it's much more relevant. But that's the only place that this whole subject had any practical implications. I'm not a pure mathematician, so this stuff about primes, so why do I care? But I love this discussion, and I think it's fun for all of us when you're thinking about something you haven't thought about in 30 years. And say, oh yeah, well, what's that? Where did that come from? So, it's lovely. I love it.
So did you use real numbers or complex numbers for that?
Complex numbers.
Complex numbers. And,
Yeah.
and it was that same summation series?
Yeah. Oh yeah.
Okay.
Because I think it's basically kind of like signal analysis, or the kind of stuff you guys are, you're trying to have communication systems. Or now when it gets to stuff like quantum computing, I don't know where the relevance is myself.
Okay, thank you for,
I'm not asking a question. I'm just posing.
okay, I didn't know about the chemistry connection, so now we
Yeah.
know.
Yeah, yeah.
Okay, the next person is Tom Forger. Please unmute yourself.
Okay. All right. I got a lot to cover here. First of all, one is not a prime because you want to have a unique factorization of integers. If you add one, it's a prime, you have a unique factorization. With regard to, can you hear me?
Yes,
With regard to Andrew Lisko, he was computing the Riemann Zeta function very high up on the critical line so that he could find like the 10 to the 20th zero. And he needed different methods to compute that high up on the line. So he would do like a whole stretch at a time, very high up on the line.
and what was the purpose of him doing that?
Well, you don't know if the Riemann hypothesis is true. And what people have done is they computed high up on the line, they go to a certain point. But if you're looking for a counterexample, for example, you might want to say, well, let's go really high up where no one has ever looked before. All right.
Okay.
Rather than, the lower region. You don't know if there is a counterexample, so you want to look very high. Analytic continuation, Bill gave a very nice summary of that. Let's see if I can read my notes here. Oh, I just want to add to it. There are certain functions that are analytic in a disk that cannot be extended at all beyond that disk. They have what's called a natural boundary. So like the unit circle might be a natural boundary. You just can't go anywhere outside it. Can't continue it at all. If you can continue an analytic function, it's unique. It's a unique continuation. I think he misspoke. He was talking about the critical line as being s equal 1, but it's actually s equal 1/2. With regard to that diagram where the thing keeps circling around, that's just going up the critical line. S equal 1/2, and looking at the complex values you get as you compute the theta function and plotting that in the complex plane. People were wondering about what is complex analysis good for. There's lots of applications. One interesting thing is if you look at the Riemann mapping theorem, that's a very nice theorem. It says that if you have what's called a simply connected region in the complex plane, it's conformally equivalent to the unit disk. No matter how complicated that shape is, you can always map it conformally onto the unit disk. I think that's all I have on this.
well, thank you very much. The next person is Alan Chenowitz.
Yes, I'm a little hesitant about introducing a note of levity into this very profound discussion.
Why not?
You heavyweight mathematicians, but
Please do.
but as I was listening to the description of Gauss going step by step up that ladder and coming to the view of, where does all this lead? I'm reminded of the rather disrespectful description of experimental physicists, and which is what I was in my former life a long, long time ago. And I remember this sort of description of an experimentalist's proof that all odd numbers are prime numbers. He starts measuring out first with number 1, prime, and then 2 prime, 3 prime, 5, that's a prime, 7, 9. Oh, well, that was an experimental error probably, because 11, 13 primes again, another little one that's a bit off, but 17, 19, well, there's enough to draw a line through that. Clearly all odd numbers are prime.
Okay. Experimental error for odd numbers.
Experimental verification.
Okay. We needed some levity. Okay. So Al Hale.
Sorry about that.
That's a good reminder of the importance of primes, Alan. A comment and a question. Factoring integers, as I'm sure many of you are aware, is a very important aspect of cryptography, and RSA assumes that factoring large integers is a computationally difficult problem. In fact, you could become world famous if you could prove that on deterministic Turing machines, you can factor integers in polynomial time. It's unknown as to whether that factoring integers is in P. On the other hand, Peter Shor, who was a mathematician at Bell Labs, he showed that you can factor integers in polynomial time on a quantum computer. So that sort of upset a bunch of people, saying that if big enough quantum computers can be built, then our current methods of encryption on the internet, like RSA, are not going to be adequate. So the NIST has embarked on a post-quantum cryptography protocol or solicitation for this that you can prove is immune to attacks by quantum computers. So there's a lot of interest in factoring, both practically and theoretically. The one question that I had for Walt is that, did you imply that if the Riemann hypothesis was true, then we could use it to devise more efficient factoring algorithms for integers?
Well, when I was researching for the connection, I came up with a lot less than the connection to quantum physics. And I sort of thought that maybe that could be the case. I can't really be sure, But I mean, certainly if you can sum all the harmonics up, you know exactly where the primes are out to infinity. And it seemed to me, by looking at the graph, that if you don't include enough harmonics, it becomes more vague as you go up the prime counting function. And it didn't follow the steps that accurately, but it did cross the center point of each step. So maybe that's a good clue as well, but I was kind of like reading into what you could do with it.
Okay.
The other thing I like to mention is Tom Fouriger. He posted a link to archive that covers the moments of the zeta function, since you asked that question. So if you check the chat, the link is there, and there's a downloadable PDF paper on that. Okay. All right. Jim Landwehr has another.
Yeah, I guess just sort of a different version of what Al was saying in response to Bill's question, why should he care? Well, Bill does care about cryptography because that's important for all of his secure financial transactions and everything else on the web. And if large numbers could be factored better than anybody knows how, then that would break the cryptography stuff that's used. And the zeta function then relates, granted in more of a theoretical way, to whether you know, you could, what you can actually do with large prime numbers. So mathematicians, I think, could argue that it's relevant. Whether it actually has any practical value in terms of the computations for cryptography or today, I don't know, but that's kind of it for me.
Okay. Are there any other questions from anybody? Anybody from the physical audience, or the ones in the back room watching on an iPhone or whatever it is? John Maheda, do you have anything to say after seeing it for the 5th time?
As I told you before, every time I hear it, I learn more about it.
Okay. I mean, it is kind of an amazing phenomenon. I mean, what mathematicians have been able to do.
Right.
So, anyway, so you know, if it wasn't for that video, I wouldn't have dug deeper into, you know, what the math behind it looks and how it really works. And there's things I was wondering all along, because I think I saw that formulation that it's equal to pi squared over 6. And I said, how do they do that? You know, and nobody ever covers that. So anyway, all right, I thank everybody for attending, and now we conclude the math meeting for today.